The universe is dying, not quickly, not dramatically, not in any way you'd notice on a human timescale, but dying nonetheless. Every star that shines is burning through fuel it can never replace. Every galaxy that glows is slowly spending its last reserves. And the universe, the entire vast, magnificent cosmos, has a clock ticking quietly in the background. A clock that started the moment everything began. And one day, in the incomprehensibly distant future, it will stop. Now, I want to be clear about something before we go further. This isn't speculation. This isn't science fiction. The fate of the universe is one of the most well-supported conclusions in all of physics. We know how this ends, not in every detail, but in its broad strokes the destination is clear. And by the end of this lecture, you'll understand exactly how the universe will die. And why, strangely, that knowledge makes the present moment more beautiful, not less. My name is Dr. James Mitchell, and this is Science Explained Properly. Let's begin. Before we talk about how the universe ends, we need to remind ourselves of something we covered in an earlier lecture. The universe has a direction, not a physical direction, not north or south or up or down, but a thermodynamic direction, from order to disorder, from low entropy to high entropy. We talked about entropy when we discussed time, the idea that the universe started in a highly ordered state and has been moving toward disorder ever since. That direction, that relentless drift from order to chaos, is what gives time its arrow. And it's also what will eventually kill the universe. Here's the key idea to hold on to throughout this lecture. The universe is running out of useful energy. Not energy in total, energy is conserved, it doesn't disappear. But useful energy. Energy that can do work. Energy that can power stars, drive chemical reactions, sustain life. Think of it like this. Imagine a room with a roaring fire on one side of it and an ice-cold wall on the other. The difference in temperature is what allows work to be done. Heat flows from hot to cold, and in that flow, you can extract energy. You can use it. But as the fire dies and the room slowly reaches the same temperature everywhere, as everything equalizes, that difference disappears. The energy is still there, spread throughout the room as heat, but it's useless. You can't extract work from a room where everything is the same temperature. The universe is that room, and it's slowly, inevitably, equalizing. Let's start part 2 of this lecture with the most visible symptom of the universe's decline. The stars. Right now, the universe is in what cosmologists call the Stelliferous Era, the age of stars. We live in it. It's the period when the universe is bright, active, and energetic, when fusion is happening across hundreds of billions of galaxies, each containing hundreds of billions of stars. It feels permanent. It isn't. Stars have a finite lifespan. We talked about this in our very first lecture. Stars fuse hydrogen into helium, helium into heavier elements, and eventually run out of fuel. When they die, their matter is scattered back into space. But here's the problem. Star formation requires cold, dense clouds of gas. When a star dies and scatters its material, that material doesn't automatically become a new star. It needs to cool. It needs to condense. And over time, over very long timescales, the raw material for new stars is gradually used up. Think of it like a campfire. You start with a pile of wood. As you burn it, some of it becomes ash, some becomes smoke, some becomes heat. You can gather the ash and try to burn it again, but it won't burn the same way. The useful fuel is being consumed, and there's no one adding more wood to the pile. The universe has a finite supply of star-forming material, and it's being spent. Current estimates suggest that the age of stars, the Stelliferous Era, will last for roughly 100 trillion years. That sounds like forever. It isn't. On the timeline of the universe's total lifespan, the age of stars is just the opening chapter. A brief, brilliant flash. We live in that flash. So what happens after the last star dies? This is where things get genuinely strange. When the last stars burn out, roughly 100 trillion years from now, the universe enters what's called the degenerate era, the age of stellar remnants. The universe at this point isn't empty. It's full of stuff, just very cold, very dark stuff. White dwarfs, the cooling embers of medium-sized stars like our Sun. Neutron stars, the ultra-dense collapsed cores of massive stars. Brown dwarfs, objects that never quite accumulated enough mass to ignite fusion in the first place. And black holes. Lots and lots of black holes. For an almost incomprehensible stretch of time, the universe will simply be these objects, cooling, drifting, occasionally interacting, in an increasingly cold and dark cosmos. But even these remnants don't last forever. White dwarfs cool slowly. Given enough time, and we're talking about timescales that make the current age of the universe look like a blink, white dwarfs cool to the same temperature as the surrounding space. They become black dwarfs, cold, dark, inert objects, essentially dead stars. Here's something fascinating about black dwarfs. They don't technically exist yet. The universe is not old enough for a single white dwarf to have cooled all the way to a black dwarf. Not one. In the entire observable universe. Even the very first white dwarfs that ever formed are still glowing, still warm, still cooling. We've never seen a black dwarf because none exist yet. But they will. Quadrillions of years from now, the universe will be filled with them. Dark, silent, and cold. But here's where the story takes its most dramatic turn. Because even as white dwarfs cool into black dwarfs, and neutron stars drift silently through the dark, the black holes remain. Black holes don't cool. Black holes don't burn out. Black holes, as far as classical physics is concerned, just sit there, consuming anything that gets too close, growing slowly, waiting. For an almost unimaginable stretch of time, black holes will be the dominant feature of the universe. This period, stretching from roughly 10 to the power of 40 years to 10 to the power of 100 years, is called the Black Hole Era. Now, I want to pause here and try to give you a sense of these numbers, because 10 to the power of 40 is not just a big number, it's incomprehensibly large. The current age of the universe is roughly 14 billion years. Written out, that's about 10 to the power of 10. The Stelliferous Era, the age of stars, ends at around 10 to the power of 14. The Black Hole Era begins around 10 to the power of 40. That's not 10 times longer than the age of stars. It's not 100 times longer. It's so many orders of magnitude longer that comparing them to human timescales becomes meaningless. The age of stars, our entire cosmic era, 100 trillion years of light and fusion and life, on the full timeline of the universe, is essentially nothing. A brief spark, a flash of light in an otherwise dark corridor. We live in that spark. Now here's where Stephen Hawking comes in, because black holes, it turns out, do eventually die. Just very, very slowly. In 1974, Hawking made one of the most remarkable theoretical predictions in the history of physics. He showed that black holes should slowly radiate energy. Not because anything escapes from inside the event horizon, nothing does, but because of quantum mechanical effects at the boundary. Here's the analogy that helps. In quantum mechanics, empty space isn't truly empty. It's constantly fizzing with pairs of virtual particles, particle and antiparticle, that pop into existence and annihilate each other almost instantly. It's like the surface of a boiling liquid, constantly bubbling, constantly creating and destroying. Now, normally this process is invisible. The particles annihilate before they can do anything. But at the edge of a black hole's event horizon, something strange can happen. One particle from a pair falls into the black hole. The other escapes. And the escaping particle carries energy away from the black hole. Over time, enormous stretches of time, the black hole loses energy. It slowly evaporates. This is called Hawking radiation. And here's the crucial part. The smaller the black hole, the faster it evaporates. The largest black holes, the supermassive ones at the centers of galaxies, will take somewhere around 10 to the power of 100 years to completely evaporate. That number has a name. A googol. A 1 followed by 100 zeros. And when the last black hole evaporates, when the very last one finally radiates away its final particle of energy, the black hole era ends. And what's left? After the last black hole evaporates, the universe enters its final phase, the dark era. And this is where the universe's story effectively ends, not with a bang, not with a collapse, but with an almost infinite, almost silent expanse of particles, scattered, cooling, drifting. The universe at this point is a thin soup of photons, electrons, positrons, and neutrinos. The last remnants of all the matter and energy that once made stars, planets, galaxies, and life. Spread across a space so vast that the average distance between particles is almost incomprehensible. Temperature, effectively absolute zero. Structure, essentially none. Change, almost nothing. This is heat death. Not heat in the sense of warmth. The name is somewhat misleading. Heat death means maximum entropy, the state where the universe has reached complete thermodynamic equilibrium, where there are no more temperature differences to exploit, no more useful energy to extract, no more work to be done. The universe isn't gone. The energy is still there, but it's perfectly, completely, irreversibly spread out. Useless. And in that state, in that final, vast, cold, dark equilibrium, time itself becomes meaningless, because time, as we discussed in our entropy lecture, is the progression from one state to another. When nothing changes, there is no time. The universe doesn't end, it just stops. Now, I want to briefly mention that heat death isn't the only possible ending. Physics gives us a few other candidates. The first is called the Big Rip. If dark energy, which is the force accelerating the universe's expansion, keeps increasing in strength, it could eventually overcome not just gravity between galaxies, but gravity within galaxies, within solar systems, within planets, within atoms themselves. Everything would be literally torn apart. The universe would end not in cold equilibrium, but in violent, rapid expansion, ripping everything to pieces. Current evidence suggests this probably won't happen, but we can't rule it out entirely. The second is called vacuum decay. This one is genuinely unsettling. The idea is that our universe might be in a metastable state, like a ball sitting in a shallow dip on a hillside. It's stable enough for now. But if something, a quantum fluctuation perhaps, nudged it out of that dip, the universe could transition to a lower energy state. A bubble of true vacuum could expand outward at the speed of light. Everything it touches would be instantly and completely destroyed. Different laws of physics, different constants. Everything we know, gone. The unsettling part? We would never see it coming. Because it expands at the speed of light, there's no warning signal that could reach us first. One moment, existence. The next, nothing. Current physics suggests our vacuum is probably stable. Probably. But it's a reminder that the universe operates on its own terms, not ours. All right, let's bring this together. We started with a simple, heavy statement. The universe is dying. And what we've found is that its death is not sudden, not violent, not arbitrary. It's the natural consequence of the same physics that allowed it to exist in the first place. Entropy increases, stars burn out, black holes slowly evaporate, and eventually, over timescales so vast they defeat human imagination, the universe reaches equilibrium. Silent, dark, complete. But here's what I want you to sit with. We live in the Stelliferous Era, the age of stars, the brief, luminous window when the universe is young enough and energetic enough for complexity to exist, for chemistry to happen, for planets to form, for life to emerge, for minds to develop that can look up at the sky and ask why. That window, 100 trillion years of starlight, sounds enormous. But on the full timeline of the universe, it's a spark, a fleeting moment of brightness in an otherwise dark and silent story. And we are in it, right now. You are alive during the most interesting chapter of the universe's existence. Not by coincidence, because complexity, like life, thought, and consciousness, can only exist during this window. Only when stars are burning, only when energy is flowing, only when entropy is still low enough that structured, ordered things like you can persist. You couldn't exist at the beginning. It was too hot, too simple. You couldn't exist at the end. It'll be too cold, too dark, too uniform. You exist here, in the middle, in the light. And that's not something to mourn. That's something to notice. Every star you've ever seen in the night sky is part of that window. Every breath you take is powered by energy, ultimately traced back to fusion, to stars doing what they were always going to do. You are not a bystander watching the universe from a distance. You are part of its most extraordinary chapter. A brief, improbable, luminous chapter. And you are in it, right now. In the next lecture, we'll turn from the universe's ending to its beginning and ask one of the most profound questions in all of science. What came before the Big Bang? But for now, look up. If you can see stars tonight, look at them, because they are burning, and their burning is what makes you possible. Thank you for listening. I'll see you in the next lecture.